In this video, we will introduce our work SymmNeRF, learning to explore symmetry prior for single-view view synthesis. Novel view synthesis is a long-standing problem in computer vision and graphics. The task is to synthesize novel views from a set of input views, which is challenging as it requires comprehensive 3D understanding. However, novel view synthesis methods usually require densely captured views as input and test time optimization, leading to poor generalization across objects and scenes. To reduce the strong dependency on dense inputs and enable better generalization to unseen objects, in this paper, we explore novel view synthesis of object categories from only a single image. Novel view synthesis from a single image is challenging, because a single view cannot provide sufficient information. Recent implicit neural representations learn scene priors for reconstruction by training on multiple scenes. Although they have shown the potential in single-view view synthesis, it is particularly challenging when the pose difference between the reference and target view is large. We observed that man-made objects in real world usually exhibit symmetric appearances. Based on this, a question arises: can symmetry priors benefit single-view view synthesis? To answer this question, we explore how to take advantage of symmetry priors to introduce additional information for reconstruction. To this end, we present SymmNeRF, a NeRF-based framework that is augmented by symmetry priors. Given a reference view, we first encode holistic representations by estimating the latent code Z through the image-encoder network. For a single query point location on array with unit-length viewing direction, we acquire its symmetric counterpart using 3D reflection symmetry property. We then obtain the pixel-aligned feature and the symmetric feature by projecting the query point and the symmetric point to the 2D location on the image plane using camera parameters, followed by bilinear interpolation between the pixel-wise features on the feature volume. The hypernetwork transforms the latent code Z to the weights of the corresponding NeRF. NeRF takes the spatial coordinate, ray direction, pixel-aligned feature and symmetric feature as input, and outputs the color and density. Finally, volume rendering technique is performed to render the color of a ray passing through the scene. Extensive experiments have been conducted to demonstrate the effectiveness of our approach. On the ShapeNet SRN dataset, our method outperforms, or at least is on par with state-of-the-art methods. We further explore our approach on the ShapeNet NMR dataset under two settings: category-agnostic single-view reconstruction and generalization to unseen categories. For category-agnostic single-view reconstruction, we train a single model across the 13 largest categories of ShapeNet. Our method outperforms other state-of-the-art methods. This implies that symmetry priors benefit the reconstruction of almost all symmetric objects. Besides, we also reconstruct ShapeNet categories which are not involved in training to generalize to unseen categories. The results suggest that our method performs comparably to pixel NeRF, which means that our method can also handle out-of-distribution categories with the help of symmetry priors. To validate the design choice of SymmNeRF, we conduct ablation studies on the synthetic chairs and cars from the ShapeNet SRN dataset. One can observe that symmetry priors injection benefits novel view synthesis. Compared with B in average performance, our full model C with the symmetric priors injection yields a performance improvement. The hypernetwork also matters. Compared with our full model C, the rendering quality of D deteriorates if we do not adopt the hypernetwork. We also visualize the comparative results on the right. As we can see, the baseline model A tends to render smoothly. Simply using pixel-aligned image features B still fails to fully understand 3D structure. In contrast, our full model C reproduces photorealistic details from most viewpoints. The rendering quality of D deteriorates as the hypernetwork is not adopted. Finally, we showcase qualitative results on different datasets. On the ShapeNet SRN dataset, as we can see, SRN is prone to generate overly smooth renderings and is unable to capture the accurate geometry, leading to some distortions. Pixel NeRF performs well when the query view is close to the reference one, but fails to recover the details invisible in the reference, especially when the rendered view is far from the reference. SymmNeRF, by contrast, can synthesize photorealistic, reasonable novel views with fine-grained details close to ground truth. To further investigate the generalization of SymmNeRF, we evaluate SymmNeRF on two real-world datasets. Here we apply SymmNeRF trained on the synthetic chairs and cars directly on the real-world images without any fine-tuning. PixelNeRF fails to synthesize reasonable novel views, because it only notices the use of pixel-aligned image features, ignoring the underlying 3D structure provided by the reference view. Compared with PixelNeRF, SymmNeRF can effectively infer the geometry and appearance of real-world chairs and cars. Results on ShapeNet and MR dataset show that our method can also handle out-of-distribution categories with the help of symmetry priors. Note that our method can also deal with objects that are not perfectly symmetric. This is because a few asymmetric objects are also included in the training dataset. Our model can perceive and recognize asymmetry thanks to the global latent code and hypernetwork. SymmNeRF therefore adaptively chooses to utilize local features to reconstruct asymmetric objects. For more details, please visit our project page. Thank you for watching.